So this is an overview of the lab equilibrium from the Connect Learnsmart Lab. In this lab, we're going to be studying the following equilibrium reaction between and this is written in the net ionic equation, so we're not worrying about the spectator ions. We have an iron 3+ ion, we have a thiocyanate ion, and when these react, they produce iron 3 thiocyanate. And we can study this reaction using stoichiometry because the different solutions have different colors. The iron 3+ ion is yellow, the thiocyanate by itself is colorless, and once they mix and the reaction starts, they start producing the iron 3 thiocyanate, which is this red color. So we can use Beer's law to determine what the concentration of the iron thiocyanate is in our solution and use that to determine what the equilibrium concentrations are of each of these species. Once we have determined what the equilibrium concentrations are of each of these species, then we can calculate what Kc is. Kc is the equilibrium expression. So for this following reaction, it's products over reactants. So our products is the iron 3 thiocyanate concentration of over our reactants, which is the iron 3+ ion and the thiocyanate ion. So we're going to do two different experiments. In experiment 1, we're going to use Beer's law to create a calibration curve of the thiocyanate ion, and we can use that to measure, once we measure the absorbance of solutions that we don't know the concentration of the iron thiocyanate, we can use our Beer's law calibration curve to calculate what the concentration is in solutions that we don't know what it is. So Beer's law is the absorption is equal to the absorptivity constant times the path length times C, where A is the absorption, that is what's measured from the spectrophotometer. C is your concentration. So in the first experiment, we know what the concentrations are because we're making the curve. And then this absorptivity times the path length, that is going to be what we find as the slope of the calibration curve. So when we plot several different concentrations versus their measured absorbances, and we get our calibration curve here. So this is going to be a line, so y is equal to mx plus b. So b should be pretty close to 0 because at a concentration of 0, you should cross the axis and end up with 0 concentration, 0 absorbance. So absorbance is our independent or our dependent variable, so it's going to go on the y-axis, and concentration in units of molarity will be our independent variable on our x-axis. So on this line, y equals mx plus b, y is going to be our absorbance, x is going to be our concentration, b should be pretty close to 0, and then m is going to be this absorptivity times path length constant. Once we have calculated what this is, in the second part of the experiment, we're going to set up a series of different concentrations initially of our two reactants, mix them together so that we are producing an equilibrium reaction that has the all three species in equilibrium. By measuring the absorption of the red color that we produced, we can calculate what C is, our concentration of our product. Then, because that is our equilibrium concentration of the product, we can use an ICE table to determine what the equilibrium concentrations are of the first two reactants and plug in all of those equilibrium concentrations into our equilibrium expression so that we can calculate what Kc is. And we're going to do this for 5 different samples and then get an average Kc. And so that will be our average equilibrium constant. So let's go look at starting out the simulator and see how we're going to go about this in the virtual lab. So in this video I'm going to go over the general idea of how to go about doing the equilibrium lab in Learnsmart Labs. So in this lab we're looking at an equilibrium reaction between two different species. One of them is going to be provided by the iron 3 nitrate, and the other one is going to be provided by potassium thiocyanate. And we're going to be looking at a reaction between these. So the first part we need to do is we're going to keep track of this reaction by how they change color between the two species. So if you follow the directions, the first thing you are to do is to make a stock solution. So you're going to make a stock solution that contains both of the species plus distilled with deionized water, and then you're going to make 3 diluted solutions and put those into the test tubes, making sure to always use a stir rod to mix. So first of all, the first thing that you need from the instructions is you need 8 milliliters of deionized water. So you're going to take the graduated pipette and put it into the deionized water and select I want 8 milliliters. Then you're going to go over the stock solution and empty it. Now make sure you do not reuse these, just like if it was a real lab, it will get mad at you if you do. So once you've used it once, it goes into the wash and you get a clean pipette each time. So the second thing you need is 10 milliliters of the iron nitrate. Put it in the iron nitrate, select I want 10 milliliters, and then pour that into your stock solution and then put it in the wash. Then the last thing you need is 2 milliliters of the potassium thiocyanate. Now, to be more accurate, instead of using the 10 milliliter pipette, we're going to use the 5 milliliter pipette because we only need 2 milliliters there. 2 milliliters, and then put it in there. And notice the color change. It suddenly turned red. And this is reminding you to mix it. So, you're going to go over here to the stirring bars and use that to mix it. Mix, 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 and then put that in the wash. So we've completed making our stock solution, and we're ready to make each of the diluted solutions as follows. So once you've made all of your diluted solutions, remembering that each time you finish making any solution, whether it's a stock or diluted, you use the stir rod to mix it up. We go on to the next step. So we're going to use iron nitrate as our blank. The reason being the iron nitrate has this yellow color, and what we're looking for is the appearance of the red color. So by using the yellow color as our blank, when we measure it, and if we will be automatically subtracting any yellow that's still there, so we're just measuring the appearance of the red color. So we're going to use the clean pipette, and this is a Pasteur pipette. If you're ever not sure what you can touch here, if you click navigation, it'll show you what these are called. So when the instructions say, for example, to use a Pasteur pipette, if you're not sure what's a Pasteur pipette, if you click on navigation, you'll see, oh, that's a Pasteur pipette. So you're going to take that, and you're going to take the iron nitrate and put it into the first cuvette. And that will serve as our blank. So first we're going to calibrate it. So now the green button appears showing that we have been calibrated. So in our instructions, the next step, once we've seen the green button saying it's calibrated, is to place the cuvette containing the stock solution, enter the wavelength of 447 nanometers, and click Measure New Sample. Save absorbance, and then go on to the next solution, measuring and saving its absorbance. Once you've measured your stock solution and the 3 diluted solutions, you're going to create a calibration curve. And then the calibration curve will give you an equation, and this is the equation that needs to go into your notebook. So in the notebook here, E times L is going to be the slope of your line. And then X is your independent variable. Your independent variable is concentration. Y, your dependent variable, is going to be the absorbance. So here is your calibration curve, and E, which is your absorptivity, times L, the path length, is going to be the slope of the line. At this point we're done, so we click End Experiment. So in this next second half of the lab, you're going to take the calibration curve that you used and use it to determine Kc, the equilibrium constant. So looking at this equilibrium reaction, we can see that we have 2 reactants, one of which is yellow and one is colorless, so overall yellow on the reactant side, and one product which is red, so overall red on the product side. So by looking at the color of the solution when it's at equilibrium, depending on how red or yellow it is, can tell us whether or not we are mostly reactants, which means we would have a very small Kc, it did not proceed very far forward at all, or we are mostly products, meaning the reaction proceeded mostly forward, so the Kc is relatively large. So in the first reaction we were making, in the first experiment, we were looking at how to make a calibration curve that would tell us the concentration based off of the absorption that we measure. But now we're going to actually make the reactions where we don't know what these concentrations are going to be because they're going to react to equilibrium, and then we are going to measure their absorbance and use that to determine what the concentrations are at equilibrium. If we know what the concentrations of everything is at equilibrium, then we'll be able to tell what the equilibrium, well, we'll be able to fill in an ice table basically and be able to calculate what Kc is, the equilibrium constant. So we're making 5 solutions as follows. So just like before, we're going to be using the pipettes. So once we have made all of them, it's asking us to calculate what our initial concentrations are of the 2 reactants. So by initial concentrations, it means before they start reacting, but after we have mixed them. So we're given here what the concentration where the solutions were before we mixed them, and then we're given what the volumes are that we mixed them to. So we're going to use the dilution equation, M1V1 equals M2V2, to calculate what our new concentration is going to be, and then record that in our notebook. So I'm going to show you how we would go about doing this just for the first solution. So the dilution equation again is M1V1 is equal to M2V2, where M1 and V1 are the molarity and volume of that species before you mixed it, and M2 and V2 are the volume and molarity after mixing. And again, this is the molarity after mixing, but before the equilibrium reaction has started. So when we go to do, if you were to go to do an ice table, this is what the molarity would be in your initial row of the ice table. So we're going to find it for both reactants, the iron and the thiocyanate. Now notice that nitrate and potassium here are just basically going to be spectator ions, so we can pretty much ignore them. So when we look at the initial solution of the iron nitrate here, we saw that it had a concentration of 2 times 10 to the negative 3rd molar. Because iron and iron, there's only one iron in there, that means the concentration of the iron ion is still going to be just 2 times 10 to the negative 3rd. So that is going to be what goes in for M1, my initial molarity here. Now V1 is my initial volume, so for all of the solutions, the initial volume for the iron nitrate solution is going to be 5 milliliters. M2 is what we're solving for. V2 is your final volume after mixing. So we added 5 milliliters. For solution 1, we added 5 milliliters of the iron nitrate, 5 milliliters of the potassium thiocyanate, and 0 milliliters of water for a total volume of 10. Notice that every one of these solutions, in this case, 5 plus 3 plus 2, always adds up to 10. So V2 should be 10 for all of these. So your molarity after mixing of the iron ion here would be 1 times 10 to the negative third, or if it does not want in scientific notation, 0.00100. To do it for the thiocyanate is going to be the same thing. Thiocyanate was also 2 times 10 to the negative third molar, and it's going to have the same volume for solution 1, but then notice that for the other solutions, your V1 is going to decrease as you go down. So V1, the volume before mixing for the thiocyanate, will be different for each one of them. So although your initial concentration of iron should end up being the same for everything, your initial concentration of thiocyanate is decreasing as you go down because you added less of it. So go ahead and fill out this whole table for your lab notebook. Alright, so now we're going to go about the actual spectrophotometer part. So just as before, you're going to use the pure iron nitrate yellow solution as your blank, and then you're going to measure the absorbance of each of the solutions that you prepared. Make sure after you fill your cuvettes, you use the wipes to remove any lint or smudges from the cuvettes before proceeding to putting them in the spectrophotometer. And again, we're going to be using the Pasteur pipettes to fill the cuvettes. Once you've finished all of the solutions, you're going to go back to your lab notebook and plug in the measured absorbances here, and then you're going to use the calibration curve to calculate what your concentration of the produced species, the iron thiocyanate, is at equilibrium, where A is your measure of absorbance and C is the concentration you are solving for. So I'm going to do a quick example of how you would go about doing one of these. So again, our calibration curve in this case is A is equal to 1269.6 C. So my measured absorbance for my first sample was 0.269. Divide both sides. And we end up with what our concentration is. But I don't think it'll let you do scientific notation, so you'll probably have to take that out of scientific notation. And that is your calculated concentration. So you would do that for each one of these. So now the next part is we're going to find the equilibrium concentrations and calculate Kc. So our reaction again is the iron plus the thiocyanate goes to make the iron thiocyanate, which is our red color, and we calculated the equilibrium concentrations of that from the absorption values and our Beer's law calibration curve. So here, if I were to write out the equilibrium expression, Kc, for this reaction, it's products over reactants. Now, in a lot of these traditional questions, what you're given is you're given initial concentrations, and I'm pulling these initial concentrations that you calculated in the first part of this experiment, and you plug and you find, or you're given the Kc rather, and then you use minus x and plus x, find what x is by plugging in here and solving for x from the given k value. We're working a little backwards here because now we're not given k. In fact, k is what we're solving for. So when we fill in the ice table, we're going to fill in what we know. Well, we know our initial concentrations of the two species because we're the ones who prepared the solutions. We know that initially we have no product, and we found that at equilibrium we did produce the product, that was the red solution, and we calculated what its concentration is. So what else then can we fill in our ice table? So the change column, if I start at 0 and went to 0.000212 molar, then I must have increased by that amount. Now these two are both reactants, so they're going to both decrease by some amount. Well, how much? Well, luckily it's 1-to-1-to-1 stoichiometry, so they're going to decrease by the same amount that our product was increased. Make sure that you don't end up with a negative concentration. If you end up with a negative concentration, that probably means that you lost a zero somewhere. So once we have this, we have the equilibrium concentrations, and we can plug them in to our equilibrium expression, and that will give us Kc. And then you need to repeat it for the other 4 remaining solutions.